Okay, thanks for being here, everyone, and those of you on Zoom. So I am talking about what has come to be known as difference in differences in lots of areas. In economics, this was introduced in a very simple case where you had a before period, an after period, a control group, and a treated group. And even in more complicated settings where you have a staggered rollout intervention in multiple periods, the name has stuck, even though as a description of the actual estimator, it doesn't necessarily fit. And actually, I'm going to talk about what I've labeled, and I think what is kind of generically called nonlinear difference in differences, which is simply going to mean that we're going to take the nature of the outcome variable seriously when we have some sort of discreteness. Okay, so this is the outline of the talk. I'm probably not going to get to the extensions part, but anyone who wants to see the full set of slides, you're welcome to those. I do want to talk briefly about the simulations and just a couple of simple applications. So this came out of interest in, I started looking at this recent literature in difference in differences, which started off being critical of what is commonly known as the two-way fixed effects model, which in economics means that you control for differences in units by putting in dummy variables for each unit, whether it's a person, a county, a school, whatever, and then you control for differences across time by putting in dummy variables for the different time periods, and then you simply add a binary indicator, a treatment indicator, and it was assumed that the effect was the same in every time period. The effect was the same regardless of when you were actually first treated, when the units were first treated. So I started looking at this problem. So the conclusions were that in general, you're going to estimate some kind of strange weighted average of 2 by 2 difference in differences, and many of them don't have any causal interpretation. And so you're averaging in estimates that do have a causal interpretation with ones that don't, and who knows what you're getting. So I started working on the linear version of this I've been working on it for a while, and produced a paper where I basically just argued that, look, you can't blame the estimation method if you're using an overly simplistic model. So basically showed some equivalences among various approaches, and if you just put in treatment indicators in the right way, you get full flexibility, and then you can figure out how to aggregate those effects later on. So it seemed natural as I was working through this to then cover the nonlinear case, because it was pretty clear by the time I finished the linear case that it was going to be mechanically very straightforward, as long as you were careful to extend this to cases where you wanted to, apply this to a binary outcome or a count outcome. I know many of you, do research where you do see these sorts of outcomes, and frankly, in economics, the approach has been to simply ignore the fact that you have a binary variable or a count and just to use a linear model. Often that gives you a pretty good answer, but if you don't have anything to compare it with, then how do you know whether it's giving you the best answer that you can give? And I'm not just talking about in terms of bias, but sometimes we tend to forget about efficiency issues, and, everything else equal, we would prefer smaller standard errors to larger ones if we can legitimately have that. So clearly, I don't think I have to spend much time on this. The notion of a fractional response, certainly in economics, like this could be the fraction of assets, that you have in the stock market, and you see like piles up at the two endpoints, and then you mostly see somewhere in between that range. Unemployment rates, poverty rates, all these things can be turned into a fraction, and where you may not see a lot of the variation over the entire range. These non-negative outcomes and like count variables are the ones that I'm probably mainly thinking of, but what we call corner solutions or a mixed variable, we have a lot of outcomes where you see a 0 and then you see a somewhat continuous range. So labor earnings would be one of these things. So for people who are unemployed, you'll see a 0 for a year, but then you'll see a fairly wide range. So you can't take, there's a recent literature on why you don't want to, add 1 and take the log, that kind of seems like a sensible thing to do. It turns out not to be a very sensible thing to do. So instead, we might want to just use models that reflect the nature of the outcome variable. We know how to use these models, right? And in cross-sectional settings and panel data settings, so why not use them in this particular setting? And the key is, you just have to convince people that you have set it up so that you're identifying interesting causal effects or interesting treatment effects. And hopefully I've done that in this paper. I should say this violates the rule of presenting work that's actually been published, but it's just been published. When I agreed to give this, it hadn't been published yet. So this is now, so you can't make any criticisms of this work, right? It's already been published. No. Okay, so if we go back to just kind of basic statistics and econometrics, the arguments for using something like a logit, or an exponential model would be that, a goodness of fit could be one reason. That doesn't usually hold much sway these days in economics, at least. A better argument is that if you're looking at things like marginal effects, like a treatment effect, that the nonlinear models can often give you something that's more plausible. Like if you estimate a linear model for a binary outcome, you'll sometimes get this, this finding that as you keep increasing the x, eventually the probability will go above 1, right? And that's a little uncomfortable, right? It's, people feel differently about this, right? Some people say, so what? I'm just trying to get the estimate on average, and others will say, you're an idiot for doing this. And, then there's everything in between. So I'm always kind of in between, right? That I think the linear model can often give you a good approximation, but why don't we try something else? But the focus, so those two considerations are still here. But really, I thought about doing this because of an underlying assumption that's used in the difference in differences literature known as the parallel trends assumption. And this has to do, this is like an unconfoundedness assumption if you were comparing it to cross-sectional analysis, except here, it's not going to be with respect to levels, it's going to be with respect to changes over time. But as some recent research has shown, and kind of formally, intuitively, we've known this, that the parallel trends assumption is not going to be invariant to transformations of your outcome variable. And so the linear parallel trends assumption, given that it's kind of this unbounded trend that we're looking at, a linear trend just keeps going, right? It may not be the best assumption if you have a bounded outcome, like a binary outcome or a fractional outcome, or for count, that it can't be below 0. So the idea is to try to come up with some simple methods. You saw that simple is in the title. Almost half of my papers have simple in the title somewhere now. It's like I'm trying to say, don't referee this too hard, right? Because it's supposed to be simple, right? Okay, so this is, as I mentioned, there's this very recent paper by Roth and Santana that shows that the parallel trends is not invariant to transformations. There's this earlier work, really interesting work by Athey and Imbens on what they call the changes and changes model. And they try to show how far you can get identifying the treatment effects without making specific assumptions about functional forms. But they show that where's that coming from? Oh, does somebody need to mute on Zoom?
You can mute.
Oh, I can mute everybody. Yeah. Sorry. Do you want to show me how to do this? Let's see.
Go to participant, I suppose.
Oh, I see.
You mute yourself.
Okay. I didn't do it. Okay. I didn't do it. Okay. Um, so anyway, in this changes and changes work, it's a two-period framework. They didn't have control variables, so it was fairly stylized, but they did show that you could get identification of the average treatment effect on the treated without making parametric assumptions. My motivation is that I really want to have more general settings, and I'm willing to make a parametric assumption in order to point identify the average treatment effects rather than just getting bounds on it. Okay, so that's basically what I do in this paper is I show that if we are willing to assume a logistic function or an exponential function, then we can actually get estimates of the average treatment effects. And then, kind of I'm realistic about this, knowing how empirical people in economics and other social sciences operate, and that is they're almost certainly going to start with a linear model no matter what. Okay, so but I'm offering this as something else you can try as a robustness check. Okay, and if you get similar answers, I don't think that's a bad thing. I think that's probably a good thing, actually. Okay. Even though, as a methodologist, you want your methods to matter, but if they don't matter in most applications. So that, yeah, this paper, okay, is the one I'm talking about. And so, because there's been a lot of interest in this staggered intervention framework, I wanted to make sure it applied to all of these cases where you have this rollout of treatment, you can include control variables, and you have some sort of discreteness in the outcome. The estimation method I focus on is what I call pooled quasi-MLE. So the quasi is because in cases where we don't have to make a full distributional assumption, we don't want to. So I don't want to assume a Poisson distribution or a negative binomial or a zero inflated or anything like that. I just want to model the conditional mean. And so the class of likelihood functions are going to be in the linear exponential family because those have this property of full robustness to distributional misspecification. Okay, so in the linear case, this was kind of the key insight that I had when I showed that doing a full two-way fixed effects where you put in, suppose you had 3,000 counties, you would put in 3,000 dummy variables, one for each county, right? Well, you're not supposed to do that with things like logit, right? Because of the so-called incidental parameters problem or probit or most nonlinear methods. So what I was able to show in the linear case is you could replace the 3,000 dummy variables with just a small number of dummy variables which indicate the treatment cohort. So in other words, you only had to control for the first period that the unit was subjected to the intervention. So if that's periods 4, 5, and 6, it's just 3 dummy variables rather than 3,000 or 10 million, depending on what your cross-section is. Though I want to be clear, the estimates are numerically equivalent. Okay, so you don't have to do the full fixed effects, you just do the cohort fixed effects. So if you can get away with a few cohort dummies in the linear case, that suggests you can now apply the same principle to basically any nonlinear model. And I just want to focus on the ones where we're estimating mean effects that can be compared directly to linear estimates. Okay. Okay, so this is the statistical problem. Okay, so I want to spend a fair amount of time on the t=2 case, because once you kind of see that, then you can kind of see it gets more complicated with more than 2 periods, but understanding this is fairly critical, I think. So I'll indicate the treatment indicator by D. This doesn't change over time. This is 1 if a unit is treated in the second time period, 0 if not. All units are untreated in the base period, in the first period. Okay, so the first period is the control period. The potential outcomes to set this up is YT0, YT1, and the time periods are 1 and 2. So the parameter of interest is in this discussion of Y average treatment effect on the treated versus the overall average treatment effect it turns out if we strengthen the assumptions, we can identify the overall average treatment effect, but I'm going to focus on this parameter because it's the one that is by far the focus in this literature. So this is the you know, I'm thinking of a population. These are random variables. I'm looking at the difference. This is the gain from treatment in the second period, okay, for a generic unit. And then we're going to compute the average of this over the treated units. Okay, so that's where the name average treatment effect on the treated comes from. In the paper, I don't impose this strong of an assumption, but I'm going to do it here just to make it easy. There's a no anticipation assumption that basically says the units under study are not changing their behavior in period one in anticipation of the policy going into effect in the next period. This, of course, is not for free, because depending on whether the policy change is a surprise. Do units see it coming? Maybe they start changing their behavior so that they could be eligible for a job training program. You know, there are various issues with this, but we have to assume it. Otherwise, especially with 2 time periods, there's really nothing we can do. Okay, you can make assumptions about how big the violation is, but let's just assume it's actually true. So this means that the outcome we observe in the first period for all units is the same whether they're going to be treated in the next period or not. Okay, so that's the one assumption. And then we're going to impose a parallel trends assumption in the untreated state. Okay, now to kind of build up to this, I want to start with what we're going to assume in the untreated state in the first time period. Okay, so this function g is a function that we've chosen, and the restrictions on it is that it's strictly increasing, and I'm going to assume it's continuously differentiable just because having derivatives makes the regularity conditions easier. Okay, so one thing about this is notice immediately, this allows for confounded assignment because it says the assignment to the treatment and the control can be systematically related to what the outcome is in the first period. So in other words, people can be selected for the job training program based on whether they have a higher or low wage in the first period. So that's the power of having 2 periods, right? If we only had a single cross-section, we couldn't allow this because we would be doing a comparison of means, and then this would make it systematically biased. So the beta being different from 0 allows for confounded assignment. Okay, so but it's kind of interesting is if G is strictly increasing, this imposes no restrictions whatsoever because, of course, if I'm looking at the 2 groups, the group to be treated and the group to be that's going to be in the control, they're just 2 means. And so this is just a way of writing a transformation of the 2 means. The assumption only has bite when we see what's going on in the second period. And so in the second period, we're going to assume that the same parameters alpha and beta and the same function g show up in the second period. And then within the index, there's just this intercept shift that represents a change over time. So I call this the index parallel trends assumption because the way this extends from the linear case is this function g. But if I didn't have the function g here, you could see that the restriction, and I'm sure this is on the next slide, but I have this bad habit of, is that when you take the difference across time, it doesn't depend on the treatment status. Okay, so that's the key here. So here's the linear case right there. So the parallel trends assumption says that the assignment D is unconfounded with respect to the trend, okay, in the untreated state. So this is the trend, the change from period 1 to 2 in the untreated state. And now if you take the difference, it doesn't depend on D. That's the key identification assumption along with no anticipation. Okay, but these are separate assumptions and they are different behaviorally. So this, for example, means that some administrator is deciding who is in the job training program. they're not basing it on what they think the gain would be over time in the untreated state. Okay, I shouldn't call it gain, what the change in the outcome would be in the untreated state. They can base it on the level of the outcome in the first period, though. Okay. Okay, so the linear assumption, the linear parallel trends might be unrealistic. So I don't want to get too bogged down in this, but I just want to kind of set up a latent variable model that you can maybe go back and look at. So how do we derive logit and probit models? Well, I know in economics, the way we often do it is we say, oh, there's something like this unobserved utility, call it Y star. And when the utility from one choice is bigger than another, you make that choice. And so that's basically determined by crossing a threshold. So the latent variable that we don't observe, that I put a star on, this follows a standard linear model where there's this error term UT that is continuous. It's independent of the treatment assignment. It's like this shock over time. And then if we assume that the U's are identically distributed over time, but they could be correlated in an arbitrary way over time, if you just kind of work out, this is the indicator function that says, I see a 1 when Y star is positive, otherwise I see a 0. The kind of standard calculation leads exactly to this model where the G function is essentially, it's like 1 minus the cumulative distribution function of U. So just taking the normal logic to get a binary response model leads us to this more general model where we have, instead of assuming G is the identity function, it's something like a logit function or a probit function or whatever your favorite CDF is, 1 minus A. Okay, so again, just to remind you, the usual parallel trends assumption holds for the index, this latent variable, but it's necessarily violated for the thing that we actually observe. But if you use a linear model for the actual binary variable, that's going to violate the usual parallel trends assumption, but it will satisfy this index parallel trends assumption, presuming that we know the actual function G. And I'm going to assume we do. Okay, so that's clearly a limitation, but one that's difficult to relax, as it turns out. Okay, so the other case that I'm really interested in is this case of non-negativity, where we see zeros in particular. And so what would an index version of the parallel trends look like in this case? Well, again, in the first period, we're going to allow the assignment D to be confounded with respect to the outcome. In the second period, again, you can see hopefully the pattern here. We're just going to add this intercept shift to allow for changes over time. And then what is the parallel trends assumption? And in this case, well, if we take the ratio, you can see that the ratio doesn't depend on D, but the difference would depend on D, right? If I just take the difference in those exponential functions, the D doesn't go away, but it goes away when I take the ratio. If I take the log and then use the approximation, this is what we would call the growth, right? So using the calculus approximation, the change in the logs is roughly the proportionate change in going from period 1 to 2. That doesn't depend on the treatment assignment. So that basically the parallel trends is in terms of the growth in the mean rather than the level of the mean. That's not to say this is the right assumption at all, right? It's a different assumption. And so if you get some sort of resiliency to changes in this assumption, I think that's actually a good thing. Okay, so identification of the treatment effect. So we observe the outcome. So the way this works is this is what the average treatment effect on the treated is, and we're going to use the obvious point that for the treated group, we actually observe the outcome in the treated state. And so the first piece is always easy to estimate because we just have to use the average for the treated sample in the second time period, okay? This is the part that's going to be hard to estimate because this is for the treated group, but it's in the untreated state. Okay, so this is where using the parallel trends assumption is going to come into play. okay, along with this. So that's the sample size for the treated units. This is then just the average. The first index means treated or not. The second is the time period. So this is the average outcome for the treated units in the second time period. Okay. Okay, so this is the one that uses both the no anticipation and parallel trends assumption. So the parallel trends assumption is this, okay, so that this is telling us what happens, in period 2. And then when we put in d equals 1, we get this expression here. Since we assume that G is known, we're able to estimate this mean as long as we can estimate alpha, beta, and gamma 2. Okay. The way to estimate alpha and beta, this is where the no anticipation assumption comes into play, because all we have to do is estimate we basically have a difference in means problem, except that it's a nonlinear transformation of the means. So this is this is our observed variable. We just in the first period we have treatment and control. If you wanted to, you could estimate this by nonlinear least squares. In practice, we're going to use something like logit, Poisson regression, something like that. At least in economics, those are the common things to do. And so then once we have identified alpha and beta using just the first time period, now we can identify gamma 2 by using the control units in the second time period. So now notice, to get the y12 bar, that's the treated units in the second time period. And now this uses the other 3 groups. Well, there are 2 groups, but there's in the first period and the second period. So because I know I don't have a ton of time, I'm just going to kind of skip, around a little bit, but you can define then a time varying treatment indicator where this is the product of are you ever treated, yes or no, that's D. And then F2 is just an indicator for being in the second time period. I didn't want to reuse D, so this comes from the factor model literature. So F2 is just the usual time dummy. So this is the thing where if you looked at your data set, you would see 0, 0 or 0, 1, right? There are just those 2 possibilities in this kind of setting. Okay, so this leads to a kind of natural imputation estimator where in the you can use the control observations and just run a regression on a dummy variable. Are you ever treated? So this acts as a control, and then this is another control, and we estimate these 3 parameters. So in the linear case, this is the regression, and we estimate those exact parameters that we need. Alpha, we obtain alpha hat, beta hat, and gamma 2 hat. And then this is the average of the units in the second time period, the treated units in the second time period. So it turns out that you can pool across all of the data, and this is the kind of traditional difference in differences regression. So this is using all of the data, and all I do is I put in a constant, whether you're ever treated, that doesn't change over time. This is just always 0 in the first period and 1 in the second, and then this is my treatment indicator. So the way I like to think about this regression is these 2 variables are control variables. They allow for the first allows for systematic differences in the treated and the control before the treatment occurs. F2 allows for secular changes over time that affect all units the same way. And then WIT is the actual treatment variable. Simple algebra shows you that this, in fact, is the usual difference in differences estimator. Okay. So as I mentioned, this turns out to be the same as the so-called 2-way fixed effects estimator, where if you choose the first unit as the base group, you put in a full set of cross-sectional dummies in place of DI. So instead of 1 dummy variable, you put in n dummy variables, or n-1. It turns out that's exactly the same estimator. Okay, so that, again, this equivalence kind of suggests a way forward for nonlinear models. Okay, so for nonlinear models, we use the robustness of the quasi-MLE in the linear exponential family. So there are only two that I'm especially interested in. One is the Bernoulli distribution, which applies to both binary and fractional outcomes. And the other is non-negative outcomes, which applies to count or corner solutions or even continuous non-negative variables. And so when you actually implement this, like if you choose an exponential mean function, after a little bit of algebra, you can show that the average treatment effect is this nonlinear function of the averages, the four averages that we know we have. We have the two averages before the intervention and the two averages after. And this actually has an interesting interpretation. You take the outcome for the treated units in the first period, and then you essentially project what would have happened. So then this is kind of a trend, if you will. This is a growth term. And so we're only going to conclude there's an effect if this is different from what we would have projected it to be based on estimating the trend using the control units. Okay, so instead of this kind of linear difference in differences, I mean, we call this nonlinear difference in differences, but obviously that's a bit of a misnomer, right? Because it's really using the means in a nonlinear way. Okay, and there's actually a similar, if you were to do a logit regression, you could write, there's a similar formula in terms of odds ratios, actually. Okay, but I won't do that here. So, so when you're actually doing this in a more complicated model, a setting, there are advantages to using the so-called canonical link function with the chosen LEF. With this group, I know I don't have to explain what the canonical link is. There are combinations, right? And the reason you get this advantage is because you can just pool the data all together and then compute the average partial effect of the treatment indicator, and you get exactly the right average treatment effect on the treated. Okay, you have to be a little careful in the nonlinear models to make sure you choose only the treated subpopulation in the second time period, but that's pretty easy to do, you know, and it gives you, most importantly, the correct standard error without having to do any work whatsoever. Okay, so I'm a Stata user, and Stata makes this particularly simple. So again, I know I put too many equations on these slides. I tried to cut them down, but it was hard. So again, all we have to do is use this model here, where G is something like a logit function or an exponential function, do exactly the same thing as we did in the linear case, pull all the data together, run a logit, Poisson regression, and then just compute the partial effect with respect to the treatment variable, not with respect to this. These again are the controls. We do the partial effect with respect to this binary time-varying treatment indicator in the second time period and then for the treated units. So that's what this is here, and you will see that this is exactly the average, what Stata calls the average marginal effect. I call it the average partial effect. Okay, but again, it's very easy to do this. Okay, so we get that standard error. Okay, so just as a reminder, these are the canonical link pairs that I know about and have actually used in one way or another. So I'm going to use a logit function. It turns out Probit probably gives a similar answer, but it still doesn't give the equivalence between the two methods, one of imputation, one of pooling across all of the data. I don't know, I kind of like there being that equivalence. So if I had to choose, I would do a logit, or I'm going to do exponential plus Poisson. I'm not going to use negative binomial because Poisson is fully robust, and this gives me this computational simplicity. So in a way, restricting it to these pairs means that you're somewhat limited in what you would do in terms. So you're not going to do a lot of, data mining to come up with the answer you want. You're going to use the linear and then hopefully maybe one of these nonlinear things and then end it at that, right? If you get similar answers, then you're probably going to be satisfied with that. By the way, I felt I needed to add this. So if you are interested in things like log odds ratios, then that is exactly what you would get as the coefficient on the treatment indicator. So the delta 2 hat, I won't go through this, but this is going to be, in the case of the exponential, this is going to be this estimated trend difference in logs. And then in the case of, this is an exponential function, the coefficient that you get on the treatment indicator is the effect on the log odds, if you prefer that, okay? In economics, and we typically do the average treatment effect, right? Like the effect on the probability, but if you prefer the log odds, then you get that directly out of this as well. Okay, so how long am I supposed to stop in 5 minutes? Yeah, okay, I'll just, okay, then I'm going to show you this and then I'll probably just jump ahead to the simulations or something. Okay, so it's very easy to add controls in this. So these controls are dated before the intervention. That prevents you from including, you know, things that you shouldn't be controlling for, like over controlling where you have X's that are affected by the intervention. And I think all I'll say is this is a way to relax the parallel trends assumption where this last term here, so I'll just look at it, this term here, this is allowing the trend to depend on observed X's. Okay, whereas if you don't have the controls, you're assuming the trend doesn't depend on anything. This relaxes the parallel trends assumption. And for those of you who know about the Callaway-Santana type work on, you know, difference in differences, this is the regression version of what they do. Okay, so I'm doing it in a pure regression framework using nonlinear functional forms. They do it in a linear framework and then do doubly robust type estimation methods. Okay, so I don't want to get bogged down in this, so I'm just going to kind of skip over. Sorry about that. And I'll spend a few minutes talking about staggered interventions and then show you a little bit of output. So things get more complicated here for sure. So here we want to have the setting where the first intervention is in period Q. It lasts through capital T. And then in each period, there can be new units treated. Okay, and this is, I'm assuming initially that there's no reversibility. So once you're in treatment, you stay in treatment. There are ways to relax that are at the very end of the slides. Okay. So the key here is, so this is the outcome, the potential outcome in time period T, if a unit is first treated in period G. So I know you deal a lot with cohort. There are cohort effects and there are calendar time effects. And so G is for the cohort and T is for the calendar time. And this is just one way of indicating a unit that is never subjected to the intervention, which means over the T time periods. So just to kind of give you a flavor of this, the treatment effects are going to be defined relative to the never treated state. So these are the average treatment effect on the treated. And so we condition on the cohort G, and we're looking at the potential outcome for that cohort. And then the R here is running from the first possible treated period for that cohort to the last. So if you think about this, this gives you a lot of treatment effects in general. So if you have a unit that's first treated in period 4 and you have 6 total periods, there are 3 treatment effects for that unit. Then you go to the next year and then there are 2 treatment effects, and then you go to the final year and there's 1 treatment effect. But there you can average these by exposure time. There are various ways to collapse that information. Okay, so the idea here is the key assumptions are a no anticipation assumption again. With staggered rollouts, I think this becomes an even more questionable assumption because units treated later know that a policy change has occurred and they may be changing their behavior. So that is potentially a problem. And then this is the conditional parallel trends assumption, which is stated in terms of the never treated state. So I'll just point out a couple of things here. Is this allows for the covariates to show up in a very flexible way. So the covariates get interacted both with the cohort dummy, which is indicating, again, when were you first treated, and they get interacted with the time dummies, and this allows for this flexible trend within the function g. So again, the function g is something like a logit or an exponential, something like that, okay? So under these two assumptions, I show in the paper, and in fact, you can relax the first one a bit, that all of the average treatment effects on the treated for every cohort and calendar time pair are identified, okay? And you can identify them using a pooled quasi-MLE, just like in the 2-period case, but now you have to put in this is a control, the x's as controls, and then the x's show up in this flexible way. And except for choosing the function g, it's hard to imagine you could be more flexible in this. You're basically saturating the equation. And of course, you could argue about the linearity in x, but that's something that we, x can be interactions and cross products and so on. Okay, so that I can actually show you some numbers, I'm just going to, sorry about this. So then there are all these, equations, and this is the equation that you wind up estimating, actually. So this is with all of the data, and you put in, again, everything shows up here. Everything above the line acts as a control. Everything below the line factors into the treatment effects directly. You're allowing the effect to change by cohort, by calendar time, and by the x's if you want to. If you deal with large cross sections, this is nothing compared to what people are doing with machine learning and non-parametrics. This is like a logit with a bunch of right-hand side variables, or a Poisson regression with a bunch of right-hand side variables. It's really not anything. I mean, people react to, they see the output when I teach this material and they see that it's this long, but then you do the margins command and it gets this long, and you focus on, that if you want to. Okay, so there's nothing really too scary about this. Okay, so let me actually go to, am I getting the green line there? So let me show you how this actually works. Okay. So I did many simulations. I'm just going to show you a few. So in this simulation, and I didn't try to rig these in any particular way. I think I'm pretty reasonable about this sort of thing. The truth is the logit. Okay, so logit should do fairly well here. But I'm going to show you how it compares with a linear analysis. So in other words, the outcome is binary. You can see the treated group. This is for the common timing case. There's 6 periods. The intervention is a period 4. So you have 3 control periods, 3 treated periods. Okay. I think these seem reasonable. There is a treatment effect. So the unconditional probabilities are about 0.315 and 0.405. N equals 500, T equals 6. Okay, so these are the targets. So these are the average treatment effects in the sample, but averaged across 1,000 replications. So these are got to be very close to the population values. And you can see, interestingly, not only does the logit do very well, but the linear model actually does very well too. And in fact, in terms of bias, there's no difference. It actually does slightly better. So even though the parallel trends is clearly violated for the linear model, on average, it's getting exactly right. Okay. So you would not see, presumably in a typical sample, you wouldn't see any difference between the linear and the logit analysis. Whether you think that's good or bad, I don't know. I would think that would be a good thing. You will see, though, that in terms of precision, the logit model actually delivers much more precision in terms of the standard errors. I mean, it's hard to actually get a reduction in standard errors like that, I mean, as a practical matter. So in terms of efficiency, it's doing well. And I didn't have time to talk about the tests for parallel trends, but this shouldn't reject because parallel trends holds in the logit model. Parallel trends is violated in the linear model, but the test has no power for picking that out. But to me, that's a good thing, because why would you want to reject when it's giving you basically the same answer? So as a logical thing, parallel trends is violated, but as a practical matter, it has no effect. Then all I did was change the time trend a little bit. And now, so you can see a lot of this stuff is very similar to before, but what I did was I made the changes over time more pronounced so that you were hitting up against the boundary a bit more. And now you can see it's a total disaster for the linear model, where the logit model is still the right one, and it's getting things right on average. And now the linear model, actually, everything changes sign. Okay, so this isn't just a precision thing anymore. It actually changes sign. This is a really bad situation because the bad news is the parallel trends test still has no power. So you're going to look at these estimates and you're not going to really know what to do, okay? I was surprised that, so I don't know what to do here, to tell you the truth, right? I mean, we have to come up with some better test of parallel trends, I guess, in order to make this distinction. Okay, last one. This is a non-negative outcome. It's actually a count variable, but it's a mixture between a Poisson and a log normal. I don't know if there's a name for that distribution, but I just wanted to kind of make it kind of weird to see what would happen. And in this case, you can see, again, the mean is correctly specified. The Poisson distribution is badly misspecified, but that doesn't matter. And so again, you can see the Poisson, the exponential is pretty much right on. There's no bias whatsoever. So this is a staggered intervention with 6 time periods. And so you get these 6 different treatment effects: cohort 4, period 4, cohort 4, period 5, and so on, okay? And you can see the precision is, I mean, it is what it is. But the linear, there are no disastrous sign changes, but you can see they're pretty badly downward biased. So this is a case where, you would still be getting the same qualitative answer, even though quantitatively the effects are quite different. The good news here is that in this case, the parallel trends test does very well in rejecting linear. So in this situation, probably this is. Sorry. I know I'm over, but I'll end this. So in this case, we would have a very good chance of picking it up, and here we wouldn't reject the parallel trends. It's a bit oversized, but it's not terrible. Okay, so I bet I did have a little application here, but I will just show you this one thing. Okay, so then you get to the real world. Okay, you can generate data all you want. This is an application that was published in the AER, the American Economic Review. So that's the best journal in economics. And this used an unfortunate incident in Buenos Aires, where there was a terrorist attack on the main Jewish center. This led the government to add additional police to every block that had a Jewish center on it, okay? So there's this exogenous treatment effect. So the outcome here is automobile thefts. And so the question is, does the added police presence reduce automobile thefts? And the answer is, so this is a common intervention. So there are 5 months here after the intervention. And you can see that it makes no difference whatsoever. So this is when you estimate one effect without allowing it to change over time. This is what happens when you estimate a separate effect to see if maybe there's a buildup or and you can see there's not much evidence. There's some noise going on here, but you can see the linear and exponential models are so close together that you clearly are not going to care about that difference, right? So I didn't know what would happen when I analyzed these data, and it turns out there's no difference in this case. In terms of, and in fact, both of them essentially, with high probability would pass the event study test as well, or the parallel trends test. And so I guess in the end, you would just say, look, they give the same answer, so I'm done, right? Okay, so sorry about that. I should, I'll stop now and